We'll be starting with our first antenna, which is the dipole antenna. We open the CST Studio 2025 version. We move on to new template. Once we are onto the new template page, we go with microwaves and radio frequency or optical antennas. Antenna. We'll be dealing with wire antennas first. So we select wire antennas. We use the time domain. These will be all the parameters. Make sure temperature is in Kelvin. We'll be designing a dipole antenna which is for a Wi-Fi or a Bluetooth frequency range, that is 2.4 gigahertz. So we add the frequency range minimum as 0 hertz and maximum as 5 gigahertz. We check the electric field, H field and far field, and we define them at 2.4 gigahertz. Next, finish. Here, once we've created this page, make sure that you save this file. We're on the landing page. I'll save it for now. So we name it as dipole underscore antenna underscore 2.4 G8Z. So save this. Now first of all, we will start by creating one end of the dipole. So we go to modeling, we select the cylinder shape, we press on it, and then we press escape. Once we press escape, we have solid 1. We rename it as cylinder 1. Now I'll show you what values that we are supposed to take for this 2.4 gigahertz. So as you can see, so here are the values that I have already derived. So we have our frequency at 2.4 gigahertz. So we get lambdas about 125 millimeters, and we take the length of one side of the dipole as about 29-30 millimeters, or less than 30 millimeters. The reasons are given here. So we use these variables: h for height 1r, radius a, gap size g, and total length l. Keeping these in mind, we fill all our values. So the outer radius will be a for cylinder 1. Now this is an important point. We have our z minimum starting from minus g by 2, going all the way from minus g by 2 to minus h. Now we press on OK. Now we add the values. What were the values? If you remember, A is 0.5 millimeters, enter. G was 1 millimeters, entered, and H was 29.4 millimeters, enter. Now if we press the space tab, we can see that we've created one end of the dipole with a space of G between. Now quickly we make another cylinder, which is cylinder underscore just 2. Again, we put in the same values A, but here's the change. Now this is for the positive z-axis, so G by 2 and G by 2 plus H. We can directly press OK, and now you can see that we have successfully created dipole antenna. Now the most important step to remember is that this all is being simulated with a material as PEC, and for the go to home, simulation. Now we choose a discrete port. Now to choose a discrete port first, we need to select which two positions will get the discrete port. So press A, select this, again press A, select this. So we've basically selected two phases of the cylinders or the wires of the dipole, and then simply press discrete port. Now whichever direction that you have tapped on first, or whichever face center you have picked, so from there to there, that will be the direction, the discrete port. Discrete port is nothing but just a wire connecting our two dipoles or our ends of the dipoles, and remember that its impedance is 50 ohms. So we've successfully created a dipole antenna. Now all that is left to do is go to home and start with your simulation. Now you can see our simulation is running. Now we've specifically designed this dipole antenna to have a resonant frequency of 2.4 gigahertz, have its bandwidth less than 2%, where the bandwidth formula can be given as so we can say that bandwidth is equal to, in our case, 2 times f2 minus f1, the whole thing divided by f1 plus f2, where f1 and f2 are the frequencies besides our resonant frequencies at which our curve intersects the 10 decibel line. I'll show you what that means in a short while. So this is the value of bandwidth, and when we talk of this in percentage, we just multiply it by 100 because this is a ratio, of course. So when you multiply this by 100, we need our bandwidth lesser than 2%. So these are the two conditions for our dipole antenna. Now let's see if we can get the exact results. Now we are done with our simulation. Now to check with our results, we go to S parameters on the left, or simply go to parameters and we press S11. Now we can observe here that on pressing move axis marker to minimum, we can observe the resonant frequency and the return losses in decibels, which is minus 15.9. That gives us minus 16 decibels as our return losses, and our frequency is 2.275 gigahertz. Now this is not what we want, because we want our resonant frequency to be exactly 2.4 gigahertz and our return losses to be greater than 25 decibels or lesser than minus 25 decibels, and consecutively our bandwidth less than 2%. Now, as we all know that the frequency is inversely proportional to the length of the antenna. So what we can do is try by experimenting and changing the values of h. So let's arbitrarily decide one value. Let's reduce it by 1.6 millimeters. So that gives us around 27.8. So 27.8 millimeters with the length of one arm. So yeah, delete the current results. Okay, and I guess we'll start by simulating. Once you've done the changes, make sure that you press F7 in order to asphyxiate with the changes, and we restart with our simulation, let it go for a while. Now we return back to our S parameters. We can see that the green one now is what we have as 2.4 gigahertz. So we got the resonant frequency, but our return losses didn't improve. They are still at minus 15.93 decibels. If we just press on show measure lines and drag this down all the way to 10 dB, somewhere around here, just double click on that and we can just press minus 10, and that's what we'll get, and then drag these to match the point of intersection. It's okay if it's not very accurate. Here we go. So now we've got our distance d, which is nothing but f2 minus f1, as 0.24429. So we can just quickly calculate 2 into d divided by 2.288 plus 2.5323. That does give an error. Let's simply swap in the value of t as 0.24429. That gives us 0.101. That is approximately 10% is what our bandwidth is. So currently, what our result shows us that we've got a 2.4 gigahertz resonant antenna dipole, which has return losses of 16 decibels and it has a bandwidth of 10%. Now we need to improve our bandwidth because we wanted to concentrate on 2.4 gigahertz and improve the return losses. Return losses are on a logarithmic scale. So when return losses are zero, it means everything is getting reflected. Higher the return losses, the greater it is being transmitted, the antenna waves. So we need to focus on minimizing the bandwidth and increasing the return losses. So for that, we'll tweak a bit few parameters and see that if we can get those parameters right. Now for a standard dipole, a bandwidth of 10 to 15% is pretty good. But if you're focusing on reducing the bandwidth to make it application specific, what we can do is go to parameters list and tweak the radius and make it even more smaller. So we've chosen 0.05 millimeters, keeping G and H exactly as our second iteration, and I've started the simulation. Now we might experience a bit shift, but all we want is a resonant frequency of 2.4 gigahertz, a good bandwidth. Less than 10% is good, between 10 and 15% is fine, and our return losses, they should be as high as possible. Greater than 16 dBs is what we are aiming for right now. So we'll go with our last one, and we can see that we have moved to 2.475 gigahertz, and we've also managed to reduce our return losses. That says that this is not but let's see if we manage to use our bandwidth. Currently D is 0. So just calculate 0. 16911 divided by 2.4 plus 2.56. 569. So we get, oh, good. And we just quickly, you can see that we've got a bandwidth of 6.8%, which is pretty good. So what we need to now do is to tweak what we have, and to get back to 2.4 gigahertz, what we do is we increase the length. It is currently at 27.8, so we might tweak it for, let's say, 28.2 millimeters, and we'll quickly simulate it. So with the new tweak, we get our minimum frequency as 2.4 gigahertz, 2.44. Our S parameters is minus 15 dBs as our return loss, and again we are getting bandwidth at 6.8%. So this is how we create a dipole antenna. We try to get a resonant frequency, so we play with the length or arm length, because it is inversely proportional to frequency. We try to decrease the bandwidth as much as possible by decreasing the size. Since these are uh, narrow field antennas, we try to decrease the radius, and for a greater return loss, we keep in account these two parameters as well. So for a standard dipole antenna, 15 decibel return loss is pretty good, and a bandwidth of 10 to 15% is optimal, but less than that is excellent. So that says that your antenna is pretty uh, application oriented, and 2.44 gigahertz is exactly what Wi-Fi and Bluetooth work on. So yeah, thank you.